Hi everybody, and welcome to exercise 3 on our list of final exam review problems. And in this question, we're going to be finding the orthogonal projection of a polynomial, in this case, onto a subspace of polynomials. Okay, and this problem comes to us in two parts. The first step to doing that is always to find an orthogonal basis for whatever space we want to project onto. And then once we have that, we can find the projection. Okay, and before we dive into this, I want to remind you kind of graphically what it is that we're doing when we find an orthogonal projection. Okay, so you can picture this subspace W, okay, as maybe, I'm just going to represent it as a plane. Okay, and the thing that we're trying to project is t squared. So you can think of that as a vector that doesn't live in this plane. It's kind of living up here maybe. Okay, so there's h of t. And what we want is the polynomial that would approximate h of t equals t squared the best that it can inside of the plane. So we kind of imagine taking this vector and projecting it straight down perpendicular. Okay, and the orthogonal projection that we're looking for would be this vector right here. Okay, I'll maybe give that the name y of t. That's the closest vector that actually lives in the subspace W. Okay, or it's the vector in W that's the closest approximation of h of t. Okay, so let's get started doing that. So we're going to start with part A, where they ask us to find an orthogonal basis for W. Okay, so this is going to be using the Gram-Schmidt process. And let's remind ourselves of the notation. So we're starting with a basis for W. We generally gave those two vectors the names W1 and W2. That's the t and the t squared. Okay, and we're going to try to take that basis and transform it into an orthogonal basis for W. Okay, so we start with the basis step when we do that. Okay, so V1 is going to be just equal to W1, which in our case is t. That's our starting point. Okay, and then V2, we had a formula for calculating that looked like W2, the square root of t, minus the inner product of W2 with V1 over the length of V1 squared times V1. Okay, and then we ask ourselves, what do we mean by inner product in this particular space? Well, they tell us that we're using the inner product, we're defining the inner product to just be the product of the integral of our functions. Okay, so really what we're being asked to calculate here then looks like this, the square root of t minus the integral from 0 to 1 of the square root of t times t. Okay, and in the bottom, the norm of t squared, that's really just the inner product of t with itself. So that's going to turn into an inner product of t, the integral of t times t, which is t squared. And that's going to get multiplied by t. Okay, and you could do these integrals by hand, but I'd prefer that you use technology. There's really no point in spending the extra time here. So if you do that, the integral in the numerator turns out to be 2/5, and in the denominator we get 1/3. That's being multiplied by t. Do a little more simplifying, and that turns into the square root of t minus 6/5 t. Okay, and according to Gram-Schmidt, that would be V2, but to make the calculations maybe a little easier later on, it's customary to ask, could we maybe scale this vector so that we don't have a ratio like 6/5 in our problem? Okay, so here's that little technique that we used a couple of times in class. Let's call this V2 tilde and ask ourselves, what could we multiply that by to get a better V2? Okay, I'm thinking multiplying through by 5 might be a good choice. So we'll take V2 to be 5 times the vector that we just calculated. That's going to turn this into 5 times the square root of t minus 6t. All right, and so what we've come up with then is an orthogonal basis that consists of those two vectors. Okay, and that's going to be our answer to part A. Okay. And once we have that orthogonal basis, we are ready to actually find the orthogonal projection. Okay, so the orthogonal projection of h of t onto w. And we kind of derived a formula for doing that as well. Okay, so y of t is going to be, and I'm going to just write out the formula before we do any calculation. The variables entered are going to look a little bit different because we labeled things differently in this problem. That would be the inner product of h with v1 over the length of v1 squared times v1 plus the inner product of h with v2 over the length of v2 squared times v2. Okay, and if we fill in the pieces, remember inner products are integrals in this case. This is going to just turn into the integral from 0 to 1 of h times v1. That would be t squared times t. Okay, over the integral from 0 to 1 of v1. So that's going to just be t squared dt. All of that's going to get multiplied by t, first vector in our orthogonal basis. Okay, and then we come over to the second term. In the numerator, we've got the inner product of h, which is t squared with v2. That vector looked like 5 square root of t minus 6t, okay, over the inner product of v2 with itself. Okay, which is going to look like that. Okay, and all of that's going to get multiplied by the second vector in our orthogonal basis. So 5 square root of t minus 6t. Okay, and again, these integrals, I'm sure you could do them by hand, but that would be pretty tedious. So strongly encourage you to use technology. And if you do that, you're going to get for this first term 1/4 for the integral in the numerator and a 1/3 down below. That's multiplied by t. And then over here, you're going to get a negative 1 over 14 in the top and a 1/2 in the bottom. That's going to be times 5 root t minus 6t. Okay, and the rest is just kind of arithmetic here. So 1/4 over 1/3 reduces down to 3/4. Okay, and then over here, those reduce down to negative 1/7. Okay, and if you wanted to, you could actually leave your answer like that. If you like simplification, you could group like terms together here, and you would discover that this reduces down to 45 over 28t minus 5/7 square root of t. Okay, there is our orthogonal projection. Okay, and if we go back to the picture for just a minute, again, the interpretation of this polynomial is it's the closest approximation to t squared in the space w. Okay, so y of t geometrically is just this vector right here in our plane that we just calculated.